Good morning, guys. Regina? Yeah. Okay. Quick announcements, because I know we have class in a little bit, so let me just get through those. Um, Today's May 4th. May the 4th be with you for those fans out there. It's Monday. It is a day 5. Oh, there's Regina. Okay. It is day 5 on the schedule. All students are reminded to sign up for 2 sessions on Wednesday for Day X. The link is listed in your email. Also, there will be a full school assembly on Wednesday at 2:15 for student government speeches. That's interesting. Okay, nice. All students are required to attend except for seniors. That's really it. Hey, anybody running for student government for next year? Any people? Mauro, you running? Nice. Others in the group? Nobody else? I saw a lot of names on peer leader lists and stuff. Nice. More. What are you running for? Do you run for anything in particular, or is it just you run for a position?
No, you just run for the student government, and the only distinct position is whoever gets the most votes, like the student body president.
And then after that, everyone's a rep.
Yeah,
There's no vice president anymore, any of that kind of stuff, right?
no.
Okay. All right. Nice. All right. I'm gonna start letting others into class because we're gonna have class in about 2 minutes anyway. You guys obviously hang out.
I'm just gonna leave and come back on a different device.
No problem. I'm gonna give a couple minutes just for others to enter right now. Okay, we're almost all here. I think we're missing one person at this point. So I brought this cardboard box here just to give you guys a quick demonstration of how you could have done that center of gravity toss. So if you recall in class, I was saying that for this to work, you need to hang something vertically, right, from one part of it so that you see where the center of mass line draws, and then trace that with like a marker or a pencil. So you're not going to have maybe this at home. Like, so I'm not assuming everybody has like rope or something like that. So when you get these kind of tasks, think about ways to improvise, right? Think about things to do. And I'm sure a lot of you did this because I saw about 10 videos coming through this morning and different cool examples, but this was just one of the samples. Like I started by thinking about like, all right, what about headphone cables, right? If I just took headphone cables and to the end of the headphone cables, I have the headphones themselves. They're somewhat massive, right? Meaning they have mass to them. And if I were to just let this hang vertically, I need to have a little bit of tension in it, right? So I'd have to tie something around the bottom of here to add a little mass. But at the top here, I could take this and where's my trusted bobby pin? I could take a bobby pin, put it right through the piece of cardboard. Now again, I didn't tear up this box because I'm about to use it to send something actually, but I would tear off one of the leaves of the box, right? And cut it in a weird shape, that amorphic shape we're talking about. Put the bobby pin right through the box. So the bobby pin is sticking out, imagine coming out of here, tying the headphones to the top, and then let that hang. I then noticed like 2 seconds later that I actually have something that's even better. So any sort of a charging cable. A charge cable will have something on the end of it usually, right? Whether it's the actual charging brick itself. So like the iPad charging cable or your computer charging cable, take something like that, take the end that is supposed to be plugged in, tie that around the pin that's going to go through. But remember, I'm using a bobby pin here. You could use a paper clip. You could use, if you have a thumbtack, you could use anything you'd like to that'll go through the paper now, the cardboard. Realistically, you could even use something like a utensil, right? You could use a fork, pop a hole in it, and then take like a skewer, like a wooden skewer, and put the skewer through, and that acts as your pivot point at the top. But the idea here is that all you need is literally something with a rope with it, and then has a weight on it, piece of cardboard that you're going to cut into the shape that you want to cut. Like I would have cut it from probably one of the side panels there, or maybe this side panel here. And then some sort, again, of a hanging focal point. So for those who struggled, because there were I think 3 or 4 of you that asked me, like, could I get a little more help? I don't have all the materials that are listed here. If you want to take a little more time tonight and send that in, improvise, right? Figure out what you have to do. That's why this is an honors physics class. So when it comes down to it like this, I get it that not everything was listed on that assignment, but I also mentioned that in class. That was one of the things I said, that this is an outline from what we would do in school. And I want you guys to adapt for what you could do at home for the materials that you have. Okay, so to give you a little background in case those were, some of you were a little bit confused, I think, on that still. That's part 1 for today. And I know a lot of you did it, so feel free to talk to each other also. Like, hey, how did you end up making that work? Not like, I want your exact apparatus and watch you make it, but what did you use? What did you use that would work reasonably? If I don't have like, a bobby pin or a paper clip or something else that would work there, what could you have used? Second thing to talk about today, I think I gave you guys a couple homework problems over the weekend, right? Yeah. For the center of mass problems. Any questions on those problems? We have a little bit more time than we usually do in class today because we're going to watch a short video and then we're going to work on a pivot lab. So I thought I'd take a moment or two to ask if there were any questions on the center of mass homework. Looks like Eduardo, right?
Yeah, what would you do for the last problem where you had to find the center of mass with the L shape?
Yeah, with the L-shaped part there. So do you remember that video we watched in class last time where the author talked about if you don't have the mass of an object, you could use its area instead? Remember he did that whole derivation. It involved the density and then the volumes and the masses all ended up canceling out and stuff. So he ended up using the fact that it was area. That's the approach you would use there. So you would have those 2 objects and you don't have their masses. So you would end up using their respective areas, the areas. And then you would treat those objects, right? And you would treat them as point masses where their center of masses are. So to demonstrate real quick, here, I got it. Instead of drawing it all out for you, let me just show you physically. All right. So we've got a Kindle and a phone, okay? So this is your L-shaped object like this. So the center of mass of the phone is right here. The center of mass of the Kindle is right here. So those locations were given in the problem. Now, because you don't have each of these masses, you can't use the mass times the XCM and the mass times the YCM for each of them. So what you have to do is use the area of this guy right here times its center of mass position in the X, the area of this one times its center of position in the X, and then divide that by the sum of the areas. So when you don't have mass of an object and the object is the same throughout, it's uniform throughout, use its area instead of mass. Okay, that's the reason it was a level 3 or 2 problem, I think it was. I forget which one, 2 or 3, simply because mass wasn't given. But because we watched that video and we went through the process of not having mass, because it's a common thing you'll see for center of mass problems, I thought you'd want to use the area for those two parts. Okay, so we just replace M with A and try it again. Maura, yeah?
So for the second problem, how come one of the points was the empty car?
How come one of the points was what?
The empty car and its like center of mass.
Because the car itself is also an object in that scenario. Right? Think about all the objects that you're finding the center of mass among. It's the empty car, and then it's the car with the people in the. It's the full car with the. Is it 2 passengers more? Right? Yeah.
Yeah.
Yeah. So when I think about this, if I were to think about this logically, let me use my phone again so you can see. Right? Okay. So here's the object. Here's the car, and now suddenly a person sits here, and a person sits here. So when you think about it, how many masses do you actually have? You have 3 masses. You have the car itself, which has its overall center of mass somewhere in the car, traditionally toward the front because the engine is there. Now, if you had an older car where the engine used to be in the back, then it's a little bit different. The trunk was in the front. So the center of mass of the car might be here. The center of mass of the first person might be here. And then the second person, its center of mass might be here. So you've got 3 different centers of mass. And you have to use mx plus mx plus mx, 1 for each mass, person, car.
Okay.
Does that make sense?
Yeah.
Because we're not just looking at the center of mass of the people, we're looking at the center of mass of the car, person system. Remember, it's always a question is what is your system that we're looking at? And it's all 3 of those objects combined. Okay, yeah, good question. All right, let's watch a short video to start. Okay, I'm going to screen share for today. Take a moment, make sure you have your sound up so you can hear it.
Good morning. If I am sitting in a canoe holding a ball with a large mass, I throw the ball to the left and it lands in the canoe, what do you think will happen to the positions of the objects?
Flippin' physics.
Nothing is going to happen. The ball lands in the canoe, so everything just stays where it is.
Well, the ball moves to the left, obviously.
Right. But nothing else moves.
Won't the canoe and Mr. P move to the right because the ball moves to the left? Sure, the ball moves to the left and the canoe moves to the right. And then I would think everything keeps moving to the right at a constant velocity after the ball lands in the canoe.
No, I don't think anything moves.
Except the ball to the left.
Except the ball to the left.
Okay, let's watch what actually happens. As you can see, the ball does move to the left, and the canoe and I move to the right when the ball is in projectile motion. But notice what happens when the ball lands in the canoe. Everything stops moving.
Oh.
Everything stops? Why is that?
Well, first off, let's define the ball, the canoe, and me as the system. Notice that the net external force acting on the system is 0. Yes, I apply a force on the ball, and according to Newton's third law, the ball applies an equal but opposite force on me. But those 2 forces are internal to the ball, canoe, Mr. P system. Therefore, there is no net external force acting on the system.
So it's really important that we discuss that what he just spoke about, the concept, right? I just spoke about the system when I was answering Maura's question. We have to recognize that forces that are occurring inside of our system do not count as external forces. So there have been a couple questions in the last like chapter and a half now where we have collisions. All of those collisions occurring are part of the system. So back from like the first pivot lab, when the ball hit the wall and the ball rebounded off the wall there, that force that the ball applied to the wall was equal and opposite to the force applied back on the ball by the wall. The same thing occurs here. He pushes this, I think it's a weighted mass, whatever, this ball, and he tosses it. The ball pushes him back, which causes the canoe to start drifting to the right. But when the ball lands and hits the boat, it hits the boat pushes back on that, which causes the boat to then stop its motion. So whenever we have an internal force, we don't have to consider it. It's not going to affect our overall momentum of the system. And we're going to carry this idea forward into the next chapter with what is part of the system.
If there is no net external force acting on the system does not accelerate. Because the system was initially at rest, the system will remain at rest.
But then why does anything move?
Right, okay, so we have to be careful here. The system remaining at rest means the center of mass of the system will not move. In terms of Newton's second law, because the net force acting on the system is zero, the acceleration of the system is zero. Therefore, because the system starts out at rest, the velocity of the system will not change, it will stay zero, and the center of the mass of the system will remain at rest.
So that was a lot there, right? He's clearly, using all these phrases that could be a bit overwhelming. So what he's saying is this. After he tosses the ball, so here's the boat, right? So imagine my phone is the boat. After Sebastian left the room, he's coming back. Okay. After he tosses the ball, right? The ball is moving this way. Well, the boat is slowly sliding that way. So the center of mass is actually changing constantly, right? But it's actually remaining the same. So let me explain that. The ball, while moving in this direction, I don't know if that's right or left for your screen right now. While the ball is moving in this direction, the boat is moving in this direction. So the change of position of both of these objects simultaneously at a specific rate that they're changing is causing the center of mass of the system to stay still. Because remember, if the ball were here, and this is the whole boat, but there's a highly concentrated mass right here, this guy's sitting here, right, and the ball, that means the center of mass is probably not in the middle of the canoe. It's probably here, actually. But when the ball gets tossed over, even though the boat is sliding left, the ball is moving to the right. So the ball's mass is becoming further to the front of the boat, which is taking the center of mass and sliding it up. But the boat is moving further this way, which takes the center of mass and moves it this way. So the ball moving this way and the boat moving that way are counteracting each other to keep the center of mass where it is physically. So let's see the mathematical analysis of this so you guys can understand why that number isn't changing mathematically, not just physically.
However, as the ball moves to the left, the center of mass of the system moves to the left relative to the boat. To be clear, the center of mass of the system moves to the left relative to the boat, but it does not move relative to the planet. Because the center of mass of the system does not move relative to planet Earth, as the ball moves to the left, everything else in the system must move to the right in order to keep the center of mass of the system in the same location relative to planet Earth.
I get that. But why does everything stop when the ball lands in the boat? Oh, I know. That is because the boat stops the ball from moving to the left. If the canoe and Mr. P kept moving to the right, the center of mass of the system would move to the right. There is still zero net external force acting on the system, so the center of mass of the system needs to stay at rest, so the canoe and Mr. P have to stop moving to the right.
Absolutely. There is a Newton's third law pair here. The ball applies a force on the canoe, and the canoe applies an equal but opposite force on the ball. Both the ball and the canoe are a part of the system, so those two forces are internal to the system, so the net external force is still zero. Now, what do you think will happen if I throw the ball, but it does not land in the canoe, it instead lands outside of the canoe?
So what do you guys think here? What will happen at this point? If he tosses the ball, but it doesn't land in the canoe. Jack, what do you think?
So since the total mass of the system's changing because it's going on in an external place, the center of mass will change.
Yeah. So that ball not hitting the canoe afterward, what'll happen is the canoe itself is probably just going to keep on drifting, right? And it's drifting more in the direction of our video to the right. So therefore, yes, the center of mass will continue to slide and move relative to the Earth because suddenly we have less mass in the system, right? We're looking at a system that has lost mass.
Well, clearly nothing changes from the first example while the ball is in projectile motion.
But the ball is not a part of the system because it does not land in the boat, right?
Right, so in this case, the system is actually just the canoe and Mr. P. Therefore, there is a net external force acting on the system, which means after the ball leaves Mr. P's hands, the canoe and Mr. P will continue to move to the right at a constant velocity. Just like before, there is a Newton's third law pair here. The force Mr. P applies on the ball is equal and opposite to the force the ball applies on Mr. P.
Right, but the ball is no longer a part of the system, so the two forces do not cancel one another out, and the net force on the system is not zero.
All right, let's see if you are correct. Will you look at that? The canoe and I do continue to move to the right, even after the ball lands outside the canoe. Unlike when the ball landed in the canoe, when the ball lands outside the canoe, there is a net external force acting on the system, the canoe and me, and therefore we continue to move to the right, even after the ball lands. Now, let's go back to the ball landing in the canoe and actually calculate how far the canoe and I move. Let's define some known values. The mass of the ball is 6.5 kilograms. The mass of Mr. P is 72 kilograms. The mass of the canoe is 33 kilograms. We have set the X position 0 location at the center of the canoe, so all X position measurements will be relative to the center of the canoe. Notice we are not concerning ourselves with the Y position center of mass because we are only discussing horizontal movements in this example. Because I do not move relative to the canoe, the initial and final positions of Mr. P are both 133 centimeters to the right of the center of the canoe. Both the initial and final positions of the canoe are 0 because the canoe does not move relative to itself, and we are assuming the center of mass of the canoe is directly in its center. The initial position of the ball is 108 centimeters to the right, and the final position of the ball is 157 centimeters to the left of the center of the canoe. Bo, please determine the initial X position of the center of mass of the system.
Okay. The initial X position of the center of mass of the system equals the mass of the ball times the initial position of the ball, plus the mass of Mr. P times the initial position of Mr. P, plus the mass of the canoe times the initial position of the canoe, all divided by the total mass of the system. Substituting in numbers gives us 6.5 times 108 plus 72 times 133 plus 33 times 0, all divided by the quantity 6.5 plus 72 plus 33, which equals 92.179 centimeters.
Notice the convenience here by letting the center of the canoe be the 0 reference line, measuring everything about the center of the canoe. It will never have an effect on the X position here. See where my mouse is highlighting here? This is always going to be 0 because if the center of the canoe is like your, like your y-axis, right? Think about your y-axis up and down. That's the 0 point along the x-axis actually. It's not going to move because the center of the canoe, even if it starts to slide, if the center of it is still the 0 point, it's always going to have its mass located at the 0 point. So this will always be 0, which is why we defined, or why the author defines, the center of the canoe as a reference point instead of like picking an arbitrary location and measuring everything from there. You could do that and that's fine. It would just change this number each time. So if you want to call the end of the canoe the location where we're starting, or another fixed position, that's fine, and this will just have a value instead each time.
Actually, the final X position of the center of mass of the system calculation is almost the same. Do you want me to do that one too?
Sure, Bo, go ahead.
The final X position equation is similar to the initial, just replace the initial with final. Also, the only value that changes is the x position of the ball. The initial position was positive 108, but now the final position is negative 157. That gives us 76.731 centimeters for the final x position of the center of mass of the ball, canoe, and Mr. P system.
Remember, our goal here is to determine the change in position of the center of mass of the system. Change in, or delta, is always final minus initial, so it is 76.731 minus 92.179, which equals negative 15.448, or negative 15 centimeters with 2 significant digits. In other words, the center of mass of the system moves 15 centimeters to the left relative to the system. In order for the center of mass of the system to stay in the same location relative to the rest of the planet, the zero reference point of the system, the center of the canoe, needs to move 15 centimeters to the right relative to the planet. As you can see in the video, our prediction matches the demonstration. And again, the physics works. The physics works. The physics works. The
It's not my fault this time.
I still think you're completely responsible.
Okay. He gets a little excited at the end there. Yeah. So the concept here again is that as the ball is tossed, right, its mass is the only thing that's changing position in this system. The canoe's mass is still at the center. Mr. P's mass is still 133 centimeters to one side. So by the changing location of the mass of the ball, it's going to cause the canoe and the center of mass of it to change its location. By how much? 15 centimeters. What I do like about this channel a lot is that this author not only proves things mathematically, but then measures them and is able to measure them with these high-speed cameras, which personally I think is where Pivot got their idea for that system, because the Pivot labs that we're doing is pretty new. It's only about a year old, and this guy has been making videos like this for like the last 10 years, where he uses super high-speed cameras, and he'll use protractors the same way on Pivot they do to measure angular changes, which we're going to do in chapter 8 actually. He'll use virtual rulers and stuff to measure how far it goes and how many frames it moves and how many frames in the video go by, so he knows how much time elapses. So the same process is applied here. With very, very high-speed cameras, we can actually analyze things without even having sensors. And it's something that we're going to see more of next year in AP Physics, where we're going to do this a good amount more. And you guys did it enough already this year, actually, a couple times with Video Vernier, where you're able to model the projectile's path for that one lab. And then we'll see a little bit more of that. Well, probably not this year, but we'll see more of that. If you did the tossing one, you were also able to track it along the way. And using those time periods, you can actually estimate the velocity changing throughout, which is kind of what they're doing in these videos and what you've done with the Pivot videos. Let me ask questions on what he was talking about, things that you want me to elaborate on, explain a bit more. Did we all see how the canoe's center of mass, or the canoe's center of mass was always at the 0 line by setting the center equal to 0 and everything measured from there? Is that Caroline? Go ahead, Caroline. You're muted, I think, Caroline. Okay.
Yeah, my question was that, like, if so the center of mass of the canoe remains the same relative to the Earth, wherever the ball is, right?
Say it one more time. The center of mass of the canoe.
The center of mass of the canoe stays in the same place relative to the Earth, no matter where the ball is. Is that sort of what he was?
No matter where the ball is. Well, the center of mass of the canoe relative to itself is always in the same place. So here's the canoe. The center of mass relative to itself is always here, right in the middle, hypothetically, assuming it's the same throughout. So that's the center of the mass of the canoe. Now, if the canoe, after the ball is tossed, starts to slide back, then the center of mass of the canoe relative to the Earth is changing. It's sliding to this direction.
Oh, okay.
Because the ball's center of mass relative to the Earth is also changing because it's sliding or flying in the other direction. So while the ball's center of mass is moving right and the canoe's is moving left, those center of mass changes are balancing each other relative to the Earth. And it's the same thing with his center of mass, because technically his center of mass is also sliding with the canoe. The thing, though, about this problem is that instead of looking at the Earth as the relative thing, he looked at the center of the canoe as the relative position to simplify matters, so that if we call the center of the canoe the 0 point and we measure everything with respect to that, then even as the canoe slides, right, even as the canoe does this, its center of mass is still lined up with our reference point that we started with, while the ball is traveling this way and while he is sliding to the right. But think about it. If the center of mass of the canoe is right there, right where I'm holding it on the phone, and Mr. P is sitting right here, even as the canoe slides, the distance between the reference line, which is here, and Mr. P, that's not changing either. Look, no matter where I move this, the gap between my fingers does not change. So his position with respect to the center of mass reference line, the canoe's position with respect to the center of mass reference line are not changing at all. It's the ball that's changing it. So in the end, the canoe as a system with respect to the earth slides 15 centimeters to the right.
Okay.
It's a different technique, and that's why I wanted you guys to see this, so you could see that you could call the origin, right, the origin, whatever you want, and that's going to be a huge impact next chapter. We're going to have to define what we call our pivot points and origins when we get to rotational stuff, and it matters what we call to be the origin here. So if you want to challenge yourself, feel free to do so. You could pick some other arbitrary location like right here to be considered the reference point or the origin, and then all three of these center of masses would have moved, right? The center of mass of the ball would be moving because the ball would be, it's hard for me to do this. Here, let's say this is the 0 line, right? So here's the actual canoe. The ball would be flying in this direction, getting closer to the reference line. The canoe would be sliding away, getting further from the reference line. Mr. P, call Mr. P this finger here, would be sliding in this direction also, away from the 0 reference line. So if you call the 0 reference line some location outside the canoe, that you are fixed on the earth, maybe there was like a pole, he could have done this. You could technically like take a pole, stick it in the ground at the end of the canoe and make that like your 0 line and measure everything with respect to that. And it would get the same answer. You would still see that the canoe would slide over 15 centimeters with respect to this new reference line instead of the center of the canoe as the reference line. So if you want to try that and change your 0 reference line and call it someplace outside of the canoe, you can do that and you could reanalyze the problem that way. Part of the Pivot Lab today is actually going to be doing that. We're going to be looking at an example with a child walking on a surfboard. And the surfboard is on the top of a lake, and the lake is pretty flat. There's no current, there's no tide, nothing like that. So the child walks on the surfboard, and as he walks on the surfboard, you could probably expect what's going to happen. As the child walks on the surfboard gets pushed back. And then when the child walks back, the surfboard pulls forward. And if you've ever done this before on like water, when you're walking on a canoe or a boat, if you walk forward on the boat's going to move back. And the same concept is applied here because the center of mass is constant because there's no external force. Now, if instead you row with the boat and you're rowing, well, the water is applying an external force, right, to you on the canoe, on the oar, which then applies it to the system. So if there's wind that comes by and catches the sails, those are all external forces. That causes boats to move because of the external force. But you walking forward, the boat's going to slide back because your force and the force back from the boat are balancing each other. They're both considered internal forces there. So what I want to do is look at the Pivot Lab, and I'm going to screen share for a moment. So give me a second just to load this so it's up. And I'm going to run through the video with you real quick so we can see it together and make sure we all know what we're doing here. So this is called Center of Mass of Boy on a Surfboard. You're welcome to load it while you're waiting if you'd want. Some of you maybe even started it. Looks like a couple of you started it. Huh? Nice, guys. Good. I'll assign it in Moodle as a homework thing if it's ever due. So if I put one of these available up early, you don't have to. You can start it early by all means, but you don't have to. Okay. So we're here. Let me go back. Screen share. Okay. So let's take a look at this video. So we've got this boy standing on top of a surfboard. I think it's like he calls it another type of board. It's not a surfboard, but one of those really high, I think, fiberglass boards that can balance. And watch what happens. So we'll just start the video so we can see it.
Go.
Okay, so we got this poor little girl who looks cold in the water. They put a little thing later on that says, what does it say? Yeah, important note. Siri and Carl both took turns walking on the board and holding the board until we recorded one shot that worked perfectly. By chance, it was Carl that was on the board. Siri was not relegated to holding the board for every shot. Looks like, I think these are his kids, by the way. He uses his kids in a ton of videos. So the point here is that first, they mark off the surfboard with tape, you'll see, if you look carefully here where I'm pointing. And the tape actually, one of these tape measurements, they'll say later on, signifies the center mass of the board. But again, what you'll notice happening here, right, is as the child walks forward, the board slides backwards. And as the child walks backwards, the board slides forward. Okay? So these are going to be the questions that this is the video that you're going to base your questions off of here. So very similar to what you saw there a little while ago, but completely up to you on the way you want to analyze it, what you want to call the origin, if you want to call the origin the left side, if you want to call it the right side, if you want to just measure how much the board changes position by relative to the boy. But spend this time in the period instead of for homework. I thought we'd do it today so you can work with a partner on it, and spend the next, 15, 20 minutes on this, and then we'll call the period at the end there. If you don't finish it, you can finish it for homework. I think I put a due date. What did I write down? The 6th. So I gave you 2 more days. So if you have questions, you can email me at some point later today, or you can call me into your, into your breakout room. So I'm going to set you up in a breakout room at this point. I'm going to put you in breakout rooms of 3. Again, please call me into your breakout room if you guys have questions. And if you have questions before it's due, please ask me, maybe tonight or tomorrow, not the day it's due. 7 by 3. Okay. I'm going to split you up, so join these rooms, please.
I think it was just, it means like it means that the center of mass of Carl is like where, like, I don't know, like like in the middle of his body, like horizontally.
The vertical doesn't matter, right? You notice because there's no
Okay.
vertical motion of the system.
And does it matter where we put like our origin point? Like, can our origin point just be at the end of at the back of the surfboard?
Yeah, absolutely.
Okay.
It's up to you to define your origin, so you can experiment with that itself. Absolutely.
And where is that black insert? There's like,
There's a couple. Remember, it's the one right in front of her face before the video even begins, before he
Okay.
begins to walk. So it looks like it's the middle of the 3 tapes. See that?
got it. Yeah.
And
Okay, so it's at like 2 meters exactly from the back of the surfboard.
So think about where your ruler is. Make sure your ruler doesn't move, right, on your screen so that you have an origin somewhere. And I mean, it's up to you, but if you're using the back of the surfboard as the origin, that's fine. That works great. You
Yeah.
follow me?
Yeah.
But don't move the ruler, obviously, as you're using it.
Yeah.
Okay. I'm going to join another room. They're asking for help right now.
Yeah.
Hi.
Hey, what's up, ladies? How's it going?
We're a little confused with number 4.
Okay. So what did you call your origin to start? Let me ask that question. Like, what are you calling the beginning point in this? Like, where are you measuring from, I should say?
We call it the little girl in the background.
Okay. So then the center of mass of the board would be 0 position to start, because the girl, see where the girl is before the video starts?
Mhm.
There's a
Mhm.
piece of tape. There's like three black tapes. The tape in the middle, that's the center of mass of the board. And that's exactly where she is in the very beginning of the video.
Mhm.
So to start the video, the board center of mass will be at a position of 0 pretty much then, which is fine. Now, you guys placed a ruler on the screen, I assume, right?
Mhm.
Yes.
So when you put the ruler on the screen, the 0 part of the ruler should line up with that exact spot, which is the center of mass of the board. Now, you're never going to move the ruler in this entire process because the ruler is your scale at this point. The problem you're going to run into is this. How are you going to measure how far the boy has moved? Did you already measure that beforehand?
Yeah.
Okay. So if the ruler 0 part is where the girl is, then the boy is technically starting at a negative position. Do you have 2 rulers on the screen then?
Oh, I lined it up with like the back of where he started and then just saw how far he walked lined up against the ruler.
And that's fine for the first part you're talking about, right?
Yeah.
Mm-hmm.
Okay. So, but my question is, if you think about your formula, the formula is mx, right, plus mx divided by the sum of m. And that'll give you the center of mass beforehand. And that equals the center of mass afterward. So we're going to need to know the x position of the boy before he starts walking and after he starts walking with respect to what you're calling the origin. So if you call the middle of the board here the origin, where is the boy before he starts walking? What is this position? It's going to be a negative position, right? And the board technically is at the 0 spot. So the center of mass of the system beforehand is going to be the mass of the boy times his negative position plus the mass of the board times its position, which is technically 0 right now. Then when the boy starts walking forward, then his position might go into the positive range and the board, its position would go into the negative range now. So depending upon what you're calling your starting point, it's going to change it. So it might be easier for you here in this problem to set the beginning of the ruler, the 0 point of the ruler, equal to one end of the board instead. Maybe the left end of the board, so that it makes the boy's position and the board's position positive the whole time. Does that make sense what I'm saying there to make life easier?
Yeah, that's how I originally did it, I think. But I'm confused about this. This might be dumb,
Sorry?
but subscript XCOM, is that just like the
Center of mass.
And is that like, I don't know, I'm just confused with like the actual solving part, like the M2 over M2. Like, can I cancel those?
No, well, because think about it. You have M1 x1 plus M2 x2 divided by the quantity M1 plus M2.
Okay, yeah.
So because it's not a factor in the bottom is being added, you can't cancel the things that aren't there. If they're multiplied, then it would work.
Okay. So for X center of mass, would that be like the mass of the boy times like the position that it's in plus the mass of the board times the position that it's in?
All divided by the sum of the masses of the boy and the board together.
But we gotta find the other mass first.
So you're going to have to leave that as your unknown, and that'll be on
Yeah.
the left side, and then that's going to equal the center of mass afterward. So you should look at this before and after. Like when the boy is not moving, and then when the boy has moved as far as possible. Those are the two instances you need to look at and set them equal to each other. Again, because there's no external force. I'm going to jump into another room. I got 2 other questions waiting. I'll come back to you guys, okay?
Right.
Sorry, another group was asking a question. I had to wait. So how are you doing, first of all?
Good.
What's the main question? Go ahead.
Well, basically, so we're on 4, and we kind of understand that we need to use the center of mass equation, but we have 2 unknowns.
What are your 2 unknowns?
XCM and M2. And we know
Okay.
that we have to find M2.
Yes, very good. But here's the thing, Jack. You have 2 instances. You have the instance before the boy starts to walk, and then you have the instance after he's walked all the way to the front of the board, right?
Yeah.
So
Oh, yeah.
if there's no external forces acting on the system, we could say that the center of mass doesn't change ever. So we could take the center of mass before the boy walked, which has M2 as unknown, the center of mass after the boy has walked, which also has M2 unknown, and set those 2 things equal to each other. And therefore, M2 is going to be the only unknown on both sides of the equation. It may be a little bit messy when it comes to solving in the end. The algebra involved, it's going to get a little bit messy, but it won't be terrible. Thankfully, the denominators are the same. So the denominators will probably just cancel out, right? Because the denominator, no matter what position he's at, is just the sum of the boy and the surfboard, right? That's all it is, the denominator. And if you look at the center of mass before the boys walked and after the boy has walked, the denominator is still going to be M1 plus M2 in both cases. So since that's on both sides of the equation, those are going to cancel on denominators, and then you only have to work with your numerators. What are you calling your starting point?
The back of the board.
Good idea. Nice. And don't move that ruler once you place it there. I'm going to go because I have 2 other questions waiting. The other groups are asking me now. I'll come back in if you have another question. Just call me back in, okay?
Yep.
Hey, what's up, guys? Ladies, how's it going?
So we're confused on question 4.
Okay. So how have we started it so far? What's your thought process?
Well, we just found, so we know we're given Carl's mass, and then we found the displacement for each of the Carl and the board, and then we know we have to solve for the board's mass, but we're confused with what X com is.
Yeah, so that's a good question. So that's the concern right now, because you would have 2 unknowns then, right? X center of mass would be unknown, and the mass of the board would be unknown. So when determining the center of mass of any system, right, we're going to take mass times position plus mass times position divided by the sum of the masses. As Carl, right, so here's the board. As Carl walks across the board, he's pushing the board back. And as he walks back, he's pushing the board forward. So the first thing you have to ask yourself is, what is your origin, right? What's your 0 reference line in this problem? And the first thing we're going to have to think about is, where would it make sense to place the ruler? If we put the ruler here and measure the 0 line as maybe the middle of the board, as Carl walks forward, the board's middle is going to go backward, which is going to now make all my x's negative for the center of the board. So instead, we could place a ruler starting at the end of the board. And if we place the ruler like this, right, at the center of at the back of the board, as the boy walks forward, the board's going to slide back. But the center of the board will still be somewhere on the ruler. It'll still be positive. And because there's no wind, and we're assuming there's no external forces here, the center of mass of the boy and board is never changing, even as the boy walks forward. Because as he walks forward, remember, the board slides backward. So the center of mass is still constant, because those 2 things, those actions are balancing each other because they're internal in the system. So we could find the center of mass before he walks. And yes, there will be an unknown. M2 is going to be unknown, right? The mass of the board. Then we could find the center of mass after he walks, still with M2 unknown, the board, if you're calling M2 the board. And since those center of masses are equal to each other, we can set those equations equal. So I would use mx1 or m1x1 plus m2x2 over m1 plus m2 before the walking occurs. Then do the same formula after the walking occurs. Your x's are going to change, right? Your positions are going to change. As the boy moves, his position changes and the board also changes. But the masses will not change for before and after. Okay, that's a starting point I'm going to give you guys. So think about, again, setting the back of the board as the 0 point of the ruler and measuring everything else with respect to that. And don't move the ruler once you set it there. Even as the board slides, right, don't move the ruler then. You're just following the very center tape mark on the board to see where the board moves to. And you're following the boy right by his like belly button, that area, that's around your center of masses, to see where he moves to left to right. Okay, I have 2 other questions right now that have been popping up. So I'm going to come back to you guys if you have another, but just call me back in, but try that first, okay?
Thank you.
On both sides. So at that point, you could just divide it out.
Hey, Mr. Al.
Hey, guys. Yeah, the denominator should be the same on both sides. Is that what Juliet just said?
Yeah, and you're setting them equal, first of all, right? And
Correct.
Then the denominators can cancel, right?
Yep, that's what Juliet, is that what you're saying, Juliet, when I jumped in? Yeah.
Yeah.
Yeah, absolutely, because even though the M2 is unknown, you still have some number plus M2 in both, so they're identical.
Right.
That's the key to this problem. When you set the center of mass as equal to each other before he walks and after he walks, the denominators do not change because the mass isn't changing.
Mm-hmm.
Okay, and then you're going to solve for the mass of the board, which should just be a linear equation at this point, right?
Yeah.
You should have combined like terms and you have a linear solution.
Okay, thank you.
Do you want to check your number? Did you get a number yet or no?
Oh, not yet.
Almost.
I could wait a minute. Nobody's calling me in yet, so.
Okay.
I got 26.1 about.
Nice. Yep. Should be right in the middle 20s, somewhere between 24 and 26. Very good. All right, I'm going to jump into another room. Take a look at the follow-up question, okay?
Okay.
Discuss the follow-up question for sure, like amongst each other. Hey guys, how's it going?
Hey, Mr. Howell, I think we just finished.
Yeah, I think we're all good here.
All right, what'd you get for number 4? I'm curious.
We got 21.77 kilograms.
Okay, yeah, it should be somewhere in the 20s. I know that. Can you step me through your part 4? Maybe each of you share a little bit of the explanation. So if George wants to start and then somebody else take over what you did so I can hear from all of you.
Yeah, so first we found that XCOM equals 0 because we got that from the video we watched.
Okay.
And then, and also you can just tell because it goes back to the original position. But also then we got, so his mass is 33.3, and then that's times 0.85 is his displacement. And then it's minus for the next one, so minus the mass of the surfboard, and then that goes 1.3 meters. And then it doesn't really matter what's on the bottom because that's just going to get multiplied by 0 anyway.
So why did you set this equal to 0, Regina or Scarlett? Why are you guys setting equal to 0 and saying it's going to multiply by 0?
We said it's like the answer, like George said for question 3. When he returns to the original position, it means the displacement is 0. So you just substitute in 0 for x.
For the second scenario you're talking about?
Yeah.
Okay, this works. Can I suggest the second way to analyze it or look at it together? I know we're going to be out of time soon anyway, but another way to look at this problem is to set the very back of the board as the origin also. And this is what a couple groups did. So to take your ruler, and here's the surfboard, right? And put the tape measure right here pretty much so that it's at the back. And right now, the boy would be here. And as the boy walks forward, the board slides backward along the ruler. And you could use the center of mass of the board as a number. The boy has its center of mass as a number. And again, as he walks forward and this happens, the boy is now here. So his center of mass changes, the board's center of mass changes, but the center of mass of the system does not change, which is why you can set it equal to 0 there at the end when you guys did. So you kind of combine those two scenarios in one by looking at the change and how far he walked and the board walked from your answers from numbers 2 and 3 logically. So consider like looking at the center of mass of the system before the walking occurs and then after the walking occurs and set those equal to each other. So you have really two equations for center of mass. Both of those would have M2 unknown. And when you set them equal, M2 could be solved for, which is the mass of the board itself. Okay, just another way of analyzing. That's what I was saying about the video today. Like the author chose the middle of the board, which is great, and that's what you guys did, and that works fine. But you could also choose the back of the board so that all of your X positions would all be positive to make it easier on you later. Okay. I'm going to bring everybody back into the room in a second, okay?
All right.
All right.
Okay, thank you.
You're welcome, guys.
Oh, hey, Mr. Howell.
Yeah.
I had a question non-related to physics.
What's up?
So for banana bread, I'm gonna try and go get all the ingredients, but in case I can, is it okay if I just like follow along and write down the recipe?
Of course, yeah. That's.
Okay, cool.
I should have made that more clear, but yeah, that was where I wrote like if you plan to bake along with me, so you don't have to. You could just watch, you know what I mean, and then another day make it yourself, and I'll obviously show you guys all the steps. It's quite a simple recipe, you'll see. So yeah,
Okay,
that's fine,
thanks.
George. Absolutely, yeah.
Mm.
Okay, welcome back. Welcome back. I know some of you are probably mid-discussion, so I apologize for pulling you back in while you're talking there. But we did get to about the full period at this point. We went almost a full hour, so I wanted to just stop at this point and mention that there were two things to point out. One, you could, if you want to, call the center of the board the origin, right? You could have done that and called this like your starting point and placed your ruler here. Or you could have placed your ruler at the back of the surfboard. And by going group to group, I noticed that some groups did it one way, some groups did it the other. And that's fine, both ways work. If you did it one way, I would recommend just for practice, you practice doing it the other way. That's a good homework practice for you to take a look at. Your answer should be in the range in the 20s somewhere. The published answer, I think, is like 25 or 23 or 24, something like that. So it should be in the 20s for the mass. And then you have just a follow-up reflection question after that. Again, please catch up on some of your pivots if you haven't. I think there might be one or two that just want to catch up on one or two of the pivot labs, so try to do that. I'm going to try to submit your grades today. So your grades today are only listed as what are called deficiencies, which is like if a student is doing nothing to report that they're not doing anything in the fourth quarter or showing up. So everybody in this class has been fine when it comes to that. So I right now have graded your first pivot lab and I'm halfway through the second, and I'm going to probably get through the second and third one today before noon. So you'll be able to see your reflected grade on there. The way I'm doing labs, just so you know, an 85 to 100 is a 3. A 70 to an 85 is a 2. A 55 to a 70 is a 1. Anything below a 55 is a 0. Okay, so it's really pretty easy for you to get a 3 if you get 85% or higher. That's only a B, that's all it is. Anything below that, though, that's still passing, meaning 70 to 85, that'll be a 2 range still. So you understand where your 2, 1, 2, 3 grade is coming from when you see that there. You could also see, I think, I'm not sure, but let me know if this is wrong, but you should be able to see Pivot Lab 1 graded. Do you see my grades that I wrote down in comments? Have you been able to see this? Has anyone checked? I did it yesterday, like 7:30, 8 o'clock. So I don't know if anyone has looked at it yet. But let me know if you can't see that. I don't know if I need to like somehow make it visible for you to see my comments or not. It's possible I have to do that, but I haven't had too much experience. This is the first time I'm using this platform myself.
If you click on the lab, you can see the grade.
Okay, so you personally can see your own grade. Perfect. Can you see the comments I've written also? I haven't written the comments for everybody. If you got 100, I didn't write comments. But if you got anything wrong throughout the lab, I wrote a little comment below it. So take a look at that. Unless it was multiple choice, then it was just a mistake. But if you made a mistake with your math, I wrote a comment like, hey, you forgot to make this negative, or you forgot this part. Okay, you're going to run out of time, and I know you have a class coming up. So again, please feel free to meet with me, send me a message. I'll meet with you during the day, and we'll have our normal office hours Wednesday and stuff, okay? But I'll see you guys for our next class on Thursday, where we're going to start Chapter 8. Please keep in mind that I did assign problem sets throughout this whole chapter still. Although we're not having a test, you still have to do your problem set. It's just practice for you. So upcoming work-wise, today your 7.8, 7.10 was due. This Pivot Lab, if you didn't finish it just now, is due on the 6th. And then your problem set 7 is due on the 8th on Friday. I don't see you on Friday, so just get it in throughout the day at some point on Friday. Okay, again, it's practice for you guys. So you're just doing Chapter 7, more practice problems that you should have kept up with. But no test on Chapter 7. We'll start Chapter 8 on Thursday. Okay, have a good day, guys.
Thank you.
Thank you.
Thank you.
Thank you.